Right, Bismillahirrahmanirrahim. Just to recap what we did last lesson, we looked at the substitution reaction of halogenoalkanes with ammonia. And for ammonia, as a nucleophile, the lone pair of electrons come from the nitrogen. Okay, so what happens is that the halogen, in this case it's bromine, is being replaced with your ammonia, NH3. Now, even though ammonia started with 3 hydrogens, but in the product, please take note that you only have 2 hydrogens left. Okay, and this is what we call an amine group, an NH2 attached to an alkyl group. Okay, ammonia is also considered as an amine, but it's a primary amine where all the bonds attached to nitrogen is attached to hydrogen. Whereas ethylamine is also a primary amine where 2 of the bonds from the nitrogen is attached to 2 hydrogens and 1 of them is attached to an alkyl group. So this alkyl group can be methyl, ethyl, propyl, or any other combination, whether you want to have branching as long as it is attached to an alkyl group. So for this reaction, it was mentioned that ammonia needs to be in excess, okay? Apart from ammonia being dissolved in ethanol. So you cannot use aqueous ammonia for this reaction. You have to use ethanolic ammonia, and ammonia which is dissolved in alcohol. And the reason for this is because if you use aqueous ammonia, the water that you use to dissolve your ammonia in will act as a nucleophile. Okay, so we want the ammonia. Now, the reason why it has to be in excess is because the product of the reaction, which is in an amine, specifically it's called an ethylamine. The ethylamine has a lone pair of electrons on that nitrogen, and this lone pair of electrons can be donated to attack another halogenoalkanes. Okay, so imagine if you have another molecule of halogenoalkanes here, this lone pair of electrons can be given or donated to the slightly positive carbon of another halogenoalkane. Okay, so that's why we want to make sure that ammonia is in excess so that amine don't have the chance to attack your halogenoalkanes, right? So that part is what I wanted you to copy down in the very last lesson. It is very important that ammonia is in excess as the product of the nucleophilic substitution reaction, which is the ethylamine, can act as a nucleophile and attack another bromoethane to form a secondary amine diethylamine. So instead of ammonia attacking, when you have ethylamine attacking as a nucleophile, you will form what we call a diethylamine. Okay. Right. Another thing about the attack of ammonia is that this part where the nitrogen donates its lone pair to the carbocation ion to form a new CN bond, okay, you will notice that there are 4 bonds around nitrogen. So usually nitrogen would have 3 bonds, okay? There are cases where you see nitrogen forming 4 bonds, but this reaction is not the case, okay? So that's why you have a positive charge here, because the nitrogen has given away its electrons. So after it has lost its electrons, or after it has given away its electrons to form this bond here, the CN bond, it develops a positive charge. Okay, so again, to remove this positive charge, we have to break one of the nitrogen-hydrogen bond, and the electrons are donated or are given to that nitrogen so that the positive charge is cancelled out by the negative charge from the electrons. Okay, so that's why we managed to restore our lone pair here. It came from the NH bond, right? Okay, so that is just showing you the SN2 mechanism. Now we want to move on to the next step of substitution reaction, which is with aqueous silver nitrate in ethanol as a method of identifying the halogen present as example by bromoethane. Okay, let me just double check if that, okay, right. So reaction with aqueous silver nitrate is also a substitution reaction. Okay, the most important thing here is the word aqueous. That means there's water in the silver nitrate. Okay, so halogenoalkanes will not react directly with silver nitrate, but actually it will react with the H2O first as a nucleophilic substitution reaction. Okay, so what happens here is that if I were to draw the molecule just to show you what's happening. So there are actually two parts to this reaction, if you want to think about it. Okay, so first what happens is that the iodine or any halogen in the halogenoalkane will be substituted with water, H2O. Okay, so water is similar to ammonia, where even though you have two hydrogen attached to the oxygen in the starting material, but in your product, you will form an alcohol. This is actually a similar reaction to the reaction of halogenoalkanes to sodium hydroxide ion as your nucleophile. Okay, so what happens is that you get an alcohol. When you form an alcohol, you end up with only one hydrogen attached to the oxygen. If you have two, that means your oxygen now forms 3 bonds. Okay, so you can see 2 bonds with hydrogen and 1 bond with the carbon, which is the new bond. And the other product would be I minus and H plus. Okay, that H plus would have come from the oxygen. Okay, so when you combine them, it becomes hydrogen iodide, just like this equation. Okay, so for this reaction, apart from the reagent where the reactant where you use aqueous silver nitrate, you only need to heat it under reflux. If you remember reflux, that's set up with your Liebig condenser being placed vertically. Okay, the great thing about reflux is that your products or your reactants, anything that is volatile, will not be able to escape. Okay, so any volatile reactants or products that would like to escape, so the moment it enters the cold region of the condenser, it liquefies, it turns from gas to liquid, and because liquid is heavy, it will fall back down due to gravity. Okay, so this is a great setup if you want, if your reaction contains volatile reactants or volatile products. Right, so that's reflux. We go back to the reaction that we were looking at just now. Okay, so this reaction, because it is water acting as a nucleophile, we call this reaction a hydrolysis reaction. So please add this onto your notes where, so hydrolysis is the breakdown of substance by water molecule. Okay, so this is the correct term. And I think there was an error or a typo previously, the one that was under sodium hydroxide. That's not hydrolysis, that's just a substitution reaction using a hydroxide ion as your nucleophile. Okay, this one you're using water as your nucleophile, so it is called hydrolysis. This reaction is similar to the nucleophilic substitution reaction of halogenoalkanes with aqueous alkali. So your aqueous alkali is either sodium hydroxide or potassium hydroxide. Most importantly, it is your hydroxide ion as a nucleophile. Okay, so it's similar in a sense that they form the same product. Both reactions will form alcohol. However, the hydrolysis with water is much slower than with the hydroxide ion. Okay, the reason for this is because of the difference in their reactivity, I guess you can say it, but we talk about which one is a better nucleophile. Okay, so if we compare a hydroxide ion with water as a nucleophile, maybe include the lone pair there so you know where the lone pair is coming from. Okay, so hydroxide has a full negative charge, whereas water has only a partial negative charge. Okay, so a hydroxide ion is a better nucleophile because it has the full negative charge, whereas the water molecule only has a partial negative charge, right? Because of this difference in the size of the charge, of course, the nucleophilic substitution rate will also differ. Okay, so hydroxide ion will be faster or quicker at attacking your halogenoalkanes compared to water. All right, so you've got the explanations there. What I want you to copy down is this diagram just to show you the difference in charges. Okay, so I repeat, in water, the oxygen only has a delta minus charge, which is a partial negative charge, whereas in hydroxide, the oxygen has a full negative charge, which is a full minus. So because of the difference in charges, the rate of nucleophilic substitution also differs. It's faster when you use hydroxide as your ion compared to using water as your nucleophile. Okay, so once you're done copying this down, please let me know. Lepas the reaction undergo hydrolysis and jadi alcohol, baru the nucleophile attack. No, the nucleophile will attack initially. So I will show you in the SN1 and SN2 mechanism. Okay, the attack is done in the first step. The second part of the reaction is the one with silver nitrate later on. Okay, so the mechanism of SN1 and SN2 is similar to your ammonia, which we will look at shortly. Are you guys done with this diagram? Okay, right. So looking at SN1 mechanism, by now I hope you already remember that SN1 mechanism work with tertiary halogenoalkanes. So I'm just going to use, just for the sake of variety, I will use iodine, iodoalkane. Okay, so we have a delta plus on the carbon, a delta minus on the iodine. So SN1 mechanism means there's only one species in the first slow step. So that means the nucleophile will attack in the second step. Okay, so what must happen in the first step? It's the breaking of the Ci bond, where the electrons in that bond will go to the iodine. So then you form a carbocation. A carbocation is a carbon with a positive charge. Your iodine is just on the side as your product for now. And don't forget, iodine iodine from a delta minus becomes iodine with a full negative charge once it gets the electron. Okay, then this is the second part where your electrophile will come into attack. So, sorry, not electrophile, nucleophile, sorry. Your nucleophile is the water, and the lone pair comes from the oxygen. So the lone pair is donated to the positive carbon, and then you form a new bond, which is a CO bond. Now, the moment oxygen donates its electrons to the carbon, oxygen now develops a positive charge. Okay, so this step is something that student always forget. So I suggest you to highlight that. Okay, carbon has lost its positive charge. However, now the positive charge is on oxygen because oxygen has given away its electrons, right? So how do I make this positive charge happy? I have to break one of the OH bonds and donate the electrons to that oxygen to form an alcohol. So that means this hydrogen that was initially formed with oxygen, once it has lost the electrons, once the bond has been broken, it becomes H plus. It no longer has an electron. Okay, so your products would be I minus from the halogenoalkane, H plus from the water. So together they combine to become HI. Okay, plus H plus I minus. So these two will become HI. All right. So please copy this down. Again, if you have remembered the steps in an SN1 mechanism, you should be familiar with the steps. They're similar. Everything is almost the same. The only thing that's different is here, where you have a positive charge on the oxygen, and then one of the oxygen hydrogen bond has to be broken so that you can donate that electron pair to the positive oxygen. And that is also how you lose one of the OH bond in water. Just like how you lose one of the NH bonds in ammonia. Okay, so please let me know when you're done copying down. Actually, I shouldn't write down the hydrogen plus here, otherwise you'll get confused. So this hydrogen plus, this hydrogen becomes a hydrogen plus in the product. This iodide ion comes from here. The next one will be SN2 mechanism. Same thing, SN2 mechanism means that there are two species involved in the first step. So that means both the nucleophile and the halogenoalkanes are present in the first step. That's when the attack happens. All right, I'll draw for you. Okay, so you're done. Thank you. So SN2 mechanism usually is for primary halogenoalkanes. So I'm just going to use a simple primary halogenoalkane, which is an iodoethane. So don't forget your details. The carbon halogen bond, CX bond, is always polar. So carbon will develop a delta plus and iodine will develop a delta minus. And then there's your nucleophile, which is your water. You must draw the lone pair. If you don't draw the lone pair, then what are you moving? Okay, you need to show electrons moving. So again, this is the slow reaction. So what happens is that the lone pair of electrons is attacking the slightly positive carbon. Now it will form a new carbon-oxygen bond, which means carbon would have 5 bonds. And carbon can only form 4 bonds. One of the bonds need to be broken, and it is the carbon-halogen bond that is usually broken. You form a transition state, where the transition state shows you the bonds that are in the process of making and in the process of breaking. Okay, so at the moment, you still have your 2 hydrogens attached to that oxygen. This is the transition state, and nothing would happen. You don't have to draw anything in the transition state. Automatically, the iodine will leave the halogenoalkane, iodine as a leaving group, and then you will have the water molecule, the carbon-oxygen bond being newly formed. Okay, again, bear in mind the oxygen has 3 bonds, so it must develop the positive charge because it has given away its lone pair. And the next step, to make this positive charge happy, you break one of the oxygen-hydrogen bond to form an alcohol. Don't forget to draw your lone pair because you've got the electrons from the OH bond, and your other products would be H plus as well as I minus. Right? So that's how you draw your SN2 mechanism. So the question is now, where is the part 2 of the reaction? Now, the part 2 of the reaction is actually not a substitution reaction, but instead it is a precipitation reaction. Okay, remember, the substitution with water is happening in aqueous silver nitrate. Okay, so your aqueous silver nitrate contains silver ions, Ag plus, and NO3 minus, right? So there's something interesting here, which is your Ag plus, silver ions. It has something to do with your qualitative analysis reactions. When you have silver ions, in the reaction mixture, and you also have iodide ions, or you have bromide ions, or you have chloride ions. Something will happen. Okay, so let me know when you have finished copying down. Okay, are you done? Okay, right. Now, this brings us to an important application, which is the testing of halogenoalkanes. I don't know if you still remember this, but when you use silver ions with chloride, you will get white PPT. With bromide, you will get cream PPT. And with iodide, you will get yellow PPT. Okay, so yes, correct. The H plus will combine with the I minus to become HI, or they will just float around because it's an aqueous solution. They will just float around as ions. Okay, don't forget in this reaction, there's also Ag plus and also an O3 minus ions. Okay, so the Ag plus will actually react or form a precipitate with the iodide. Right, so that has an important implication, because when we see precipitate, it's something that we can observe. So if it's something that we can observe or see, we can use this as a test. Okay, so say if I didn't know what my halogenoalkane was, I didn't know if it contains iodine, bromine, or chlorine. But what I can do is that if I add silver nitrate, first the aqueous, with the water molecule in the aqueous of my silver nitrate, will attack my halogenoalkane. Okay, my carbon iodine bond will break, or my carbon halogen bond will break. So whatever halogen I form here will react with Ag plus to give me a precipitate. And whatever the color of the precipitate is, will tell me what was present in the halogenoalkane. So that's why I say that there's two parts to this reaction. Okay, so the halogenoalkanes have different rates of hydrolysis. It's great because it's something that we can see, it's something that we can observe. We can take the time for the precipitate to be produced. Okay, so we can study the rates of the reaction. And this reaction can also be used as a test to identify the halogens that are present. It depends on the color of the precipitate that you see or that is being produced. That precipitate can tell you or give you an insight of which halogenoalkane was present. Okay. So reacting halogenoalkanes with aqueous silver nitrate solution will result in the formation of the precipitate. So what this precipitate was is actually AgCl for chloride. If it was a bromide, it would have been silver bromide. And if it was an iodide, it would have been silver iodide. Okay, so these are ions actually. The Ag comes from silver nitrate, and then the halogens come from the halogenoalkane, right? So this is a great application actually. So that brings us back to the earlier part where I skipped on page 2. Okay, so if we go back to your notes on page 2, where it says aqueous silver nitrate. Okay, so this is the reason why, right? The silver ions will react with the halogens, the halide ions that are produced during hydrolysis. Okay, so I will not, I don't want to rush this, okay, because you need to copy down the equation and some more. So I think that is all for today. Okay, so in the next lesson, we will continue just to finish off this reaction with aqueous silver nitrate, and then we will finish off this topic by looking at the last type of reaction of halogenoalkane, which is the elimination reaction. Okay. Right, before you go, is there any question regarding what we just covered?